Hello everyone and welcome to the Intermediate Algebra video lectures. My name is Professor Hunter, and in this course we will be covering a variety of different types of functions, and each chapter is going to focus on a different type of function. So in the previous course in Intro Algebra, or in whatever previous math course you have taken, you covered a lot of linear equations, which are a type of function known as polynomials. So this first chapter we are going to be focusing on the type of function called polynomials. However, in order to really work with polynomials, understand what they are, and most importantly, how to perform operations on them, we do need to talk about a key component of polynomials, which are called integer exponents. So just as a recap of some basic algebra vocabulary that we are going to be using throughout this course, a variable is any letter that represents an unknown number. And it really can be any letter. We typically stay away from the letters lowercase e, lowercase I, and O. I think the reason we avoid O is kind of obvious. It does look like a 0. The reason why we avoid E and I, you're going to cover in college algebra. But other than those three, we can use any letter to represent an unknown number. Now, a constant is another name for a known number. And when you have a number and a variable attached to each other with hidden multiplication, the number in front of the variable is called a coefficient. So a coefficient is a number that appears next to a variable and is attached to that variable with multiplication. Now, an algebraic expression is an expression that combines variables, constants, and arithmetic operations. Now, algebraic expressions come in all shapes and sizes. Some of them can be as simple as 3x. That is an example of an algebraic expression. It combines the variable x, the constant 3, and the arithmetic operation multiplication. But in an algebraic expression, you can have what are called multiple terms. Terms in an expression are variables and or constants that are separated by either a plus sign or a minus sign. So for example, the expression 3x plus 4 has two terms. 3x is considered a single term because anything attached with multiplication is considered all one single term. Terms are only separated by plus signs or minus signs. So in 3x plus 4, 3x would be one term. The plus sign would separate them into two terms, and 4 is its own term. Now, algebraic expressions can have one term, two terms, they can have three terms or more terms. So this is an example of the type of polynomial that we're going to cover in this chapter. The x cubed is one term. The plus sign separates it 2x as its own term, and the minus sign separates the 3 as its own term. So this expression would have three terms. So terms are only separated by plus signs and minus signs. Anything attached with multiplication is considered all one single term. Now, the focus of this first video lecture is going to be exponents. Exponents are a condensed way of writing repeated multiplication. So for example, if you have the number 3 times itself 5 times, you can write that repeated multiplication as 3 to the 5th power. 3 to the 5th power is called an exponential, or we say that it is written in exponential form. So an exponential expression is any expression that contains an exponent. Now, an exponential expression has two parts. We have the larger number here on the bottom, which is called the base. The base is what number is being multiplied by itself. The exponent, or power, is the number of times that the base is being multiplied by itself. So the exponential 2 to the 4th power is the base 2 times itself 4 times. So if you wanted to, you can rewrite this exponential as repeated multiplication. You could write this as 2 times itself 4 times. Exponents are not the same as just regular multiplication. If you were to do 2 times itself 4 times, you would get 16. That is very different than just multiplying 2 times 4, which is 8. So exponents are repeated multiplication. The base indicates what is being multiplied by itself. The exponent is the number of times it is being multiplied by itself. Now, a couple of special exponents that we're going to cover and just get out of the way right now are exponents of 1 and exponents of 0. Now, for any real number x to the power 1 is equal to itself. So That basically means that anything raised to the power 1 is itself. That's also very important because if you see a variable that with no exponent, if you do not see an exponent, you can always assume that there is an exponent of 1 there that is not written. We typically don't write the exponent of 1 since anything to the power 1 is itself, but you can always assume that any variable that does not have an exponent has an exponent of 1. Now, another exponent that we're going to encounter all the time is 0. Almost anything raised to the power 0 is 1. So for any real number x, x to the power 0 is equal to 1. The exception is 0 to the power 0. We're not even going to go there. That's not this course. But anything else raised to the power 0 is equal to 1. Now, what we're going to be doing in this first chapter here is we are going to be taking two polynomials and we're going to be adding them, subtracting them, multiplying them, and dividing them. Before we can do those operations on these types of functions, we need to cover what are called exponent rules. So when you're performing operations on exponential expressions, such as multiplication and division, you're going to use various rules to combine their exponents and simplify them. So basically what these exponent rules are is when you take two exponential expressions and let's say multiply them together, these exponent rules will give you a really quick and simple way to combine their exponents so that you can simplify it down. So the rules for exponents apply to multiplying exponentials, dividing exponentials, raising exponentials to other powers, and raising products and quotients to powers. And those are all of the exponent rules that we are going to cover in this video. So, before I give you the product rule for exponents, I am going to take a few minutes to show you where this first exponent rule comes from. This way you have an understanding of why the product rule for exponents works the way it does, and hopefully you will be able to remember it and differentiate it from some of the other exponent rules. So the product rule for exponentials applies when you take two different exponential expressions and you multiply them together, such as x to the third times x to the fifth. These are two different exponential expressions that happen to have the same base, and that's actually going to be important in a little bit, and you are multiplying them together. So again, there is a way to very quickly combine these and very quickly simplify these. That is the product rule for exponents. However, before I give you that rule, I want to show you where the rule comes from and why it works the way it does, so that you can have an understanding of why we do this. So what I'm going to do for each of these exponential expressions is I'm going to write them as repeated multiplication. So I'm going to write x to the third as x times itself 3 times. Then I'm going to multiply it by, I'm going to do the same thing for x to the fifth. I'm going to write that as x times itself 5 times. Now, since all of these are the same, we have x and we have a ton of multiplication, and you might remember from previous courses that order doesn't really matter with multiplication. So what I'm going to do is I'm going to simplify this and write this repeated multiplication as an exponent. So what am I multiplying by itself? Well, I'm multiplying x by itself, so my base is going to be x. The exponent is the number of times that we multiply it by itself. So how many times in total have we multiplied x by itself? Looks like we've multiplied it by itself 8 times. So this will simplify down to x to the power 8. Now, I want you to look, I'm going to do the next one, but what I want you to do is I want you to look for a really fast way to go from start to finish without having to do any of this repeated multiplication work in the middle. You're looking for a shortcut. That shortcut is going to be the product rule for exponents. So I'm going to do the same thing with this next one. I have two exponential expressions, y to the second power, which is also read as y squared, times y to the fourth power. I am going to simplify these first by rewriting them as repeated multiplication. So I'm going to write y squared as y times y. Then I'm going to rewrite y to the fourth as y times itself 4 times. Then, what am I multiplying by itself? I'm multiplying y by itself, so I can take this repeated multiplication and condense it down into an exponential with base y. And then how many times in total have I multiplied y by itself? Looks like I've multiplied it by itself 6 times. So I can simplify that down to y to the 6th power. So what is a really fast way to go from start to finish without having to do any of that work in the middle? If you notice, you just add the exponents. 2 plus 4 gives you 6, and 3 plus 5 gives you 8. So that is going to be the product rule for exponents. If you take two exponential expressions with the same base and you multiply them together, you can simplify by adding their exponents. The key is the bases need to be the same, because that is the only reason why we were able to take this entire repeated multiplication and condense it down to a single exponential. So if you have some exponential x to the power a times another exponential x to the power b, because their bases are the same and we are multiplying them together, we can simplify it to x to the power of a plus b. So if you have two exponentials with the same base that are being multiplied together, you can simplify it by adding their exponents. So what we're going to do is we're going to simplify each of these, and we're going to write them as a single exponential if possible. So we're going to take the expression 2 to the third and we're going to multiply it by 2 to the fifth, and we're going to write that as a single exponential. So let's check. These two have the same base. So because they have the same base and they are being multiplied together, I am going to simplify by adding their exponents. So I'm going to keep the base the same 2, and I'm going to add the exponents. 3 plus 5 gives you 8. Now for this next one over here on the top right, with exponents, if the base of your exponential is negative, you do need parentheses around it, and I cannot stress that enough. So yes, there is a reason why in each of these exponentials the negative 5 is in parentheses. Because when the parentheses are there, that indicates that both the negative and the 5 are being squared, and then same thing here. These parentheses indicate that both the negative and the 5 are both being raised to the power 8. If the parentheses weren't there, that would mean that only 5 is being raised to the second power and this negative is considered separate, because if you remember order of operations, exponents come before multiplication. So if there are parentheses around your negative to begin with, even when you simplify, you need to leave the parentheses there. So my base, since these two bases are the same, my base is going to be negative 5 with parentheses around it. And then because we are multiplying these two exponentials together, I am going to simplify by adding their powers. So 2 plus 8 will give us 10. So negative 5 to the power 10 will be your simplified answer. Now for this next one, for m to the fourth times m, remember, if you do not see an exponent on a variable, you can always assume that there is a 1 there. So this is m to the fourth times m to the power 1. These are two exponentials with the same base m, and they are being multiplied together. So because we have two exponentials of the same base being multiplied, I'm going to simplify by adding their exponents. So I'm going to keep the base the same m, and I'm going to add their exponents. 4 plus 1 will give us m to the power 5. Now for this next one, for x squared times y cubed. Cubed is another way that you can read y to the third power. Can we combine these using the product rule for exponents? And unfortunately, the answer is no, because the base of this first exponential is x, the base of the second exponential is y. The only reason why product rule for exponents works is if the bases are the same, you can write this whole string of repeated multiplication as a single exponent. Unfortunately, that is not going to work here. So because these two bases are not the same, this is actually fully simplified as it is. So we cannot combine these further into one exponential with one single base and one single exponent because the two bases are not the same. Now, A lot of people, unfortunately, mix up the product rule for exponents with this other rule, the power rule for exponents. So I want to emphasize that the product rule for exponents has a product. So if you were taking two different, separate exponential expressions and multiplying them together, you add their exponents. The power rule for exponents is in a slightly different scenario. This is taking an exponential expression such as x squared and raising it to another power. So this is taking x squared and raising it all to the third power. And the reason that the parentheses are there is to indicate that everything in the parentheses is all being grouped together and all being raised to the third power. So what I'm going to do is, once again, before I just give you the power rule for exponents, I'm going to show you where the rule comes from and why it works. This way, hopefully, you will not only remember it, but also differentiate it from the product rule for exponents. So what I'm going to do, the parentheses indicate that everything in the parentheses is all being raised to the third power. So I'm going to expand this third power as repeated multiplication. I am going to write this as x squared times itself 3 times. And you might remember from the product rule for exponents that we just covered, if you take exponential expressions and you multiply them together, as long as they all have the same base, which they do, you can add their powers. So that'll give you x to the power 6. So just looking at this, what is a really quick way to go from start to finish without having to do any of this work in the middle? You might notice that 2 times 3 gives you 6. So that's the power rule for exponents. If you take an exponential expression and you raise it to another exponent, you can simplify by multiplying the powers. So if you have the expression x to the a and you were raising it to the power b, you can simplify by multiplying the powers. So this will be x to the power of a times b. So if you have a power raised to another power, you can simplify by multiplying the powers. The key with power rule for exponents is it always contains parentheses. So what we're going to do for each of these is we are going to simplify them and we are going to write them as a single exponential. So we have p to the fourth all raised to the power 5. So this is an example of an exponential expression, p to the fourth, and then all of that together is all being raised to the 5th power. So let's try our power rule for exponents. We have a power raised to another power. That means that we can simplify by multiplying the powers. 4 times 5 is 20. So then we're going to do the same thing here. For 2 to the third raised to the power 2, we have a power raised to another power. So I'm going to simplify by multiplying the powers. This will give us 2 to the 6th. Now remember, if at any point you want to try a problem before I do it, just feel free to pause the video and then resume when you are done working to check your answer. So if you wanted to try the next two, go ahead and pause the video and then resume when you're done. But for this next one, for x to the 5th raised to the power 2, I have a power raised to another power. So I'm going to simplify by multiplying the powers. 5 times 2 gives you x to the 10th. And then for this last one, I have y to the 6th all together being raised to the power 7. So if we have a power raised to another power, we can simplify by multiplying the power. 6 times 7 is 42. Now, the quotient rule for exponents involves you taking two exponential expressions and dividing them. So you'll have one exponential divided by another. And you'll notice here that in each of these, the bases are the same. Once again, that is actually going to be very important for this rule. And then once again, before I just give you the quotient rule for exponents, what I'm going to do is I'm going to show you where the rule comes from and why it works the way it does. So hopefully you will be able to remember these. So what I'm going to do for x to the 6th divided by x squared, you can always read fractions as division because fractions are the same as division. So you can read this as x to the 6th divided by x squared. What I'm going to do is I'm going to take both the numerator and the denominator and I'm going to write them both as repeated multiplication. So I'm going to write x to the 6th as x times itself 6 times. Then I'm going to do the same thing to the denominator. I'm going to write x squared as x times itself 2 times. Now you might remember from in whatever math course you covered fractions in, is that if the numerator and the denominator have a common factor, you can divide both the top and the bottom by that common factor, which is effectively canceling out the common factor between the numerator and denominator. That's how you reduce fractions to lowest terms. You may also remember that anything divided by itself is 1, and that does apply to variables. So if you notice here, we have an x in the numerator and another x in the denominator. And because everything on both the top and the bottom of this fraction is all multiplication, that means that these x's that I have just circled are considered common factors. So what is x divided by x? X divided by x is 1. So what basically happens is they cancel out. And we also have another pair of common factors, this x right here and this x right here. So because these are common factors, I'm going to go ahead and cancel out the common factors. And you could keep doing that until you run out of x's or variables on either the top or the bottom. So since we've run out of variables in the denominator, I'm just going to multiply what's left over. Now also remember that when they cancel out, they don't go away, they become 1 because anything divided by itself is 1. So I'm going to multiply what's left over in the numerator. So I have 1 times x times x times x times x. Well, x times itself 4 times is x to the 4th. And then the denominator is just 1, and anything divided by 1 is itself. So I don't even need to write the 1 in the denominator. This can simplify down to just x to the 4th. So remember, x to the 4th over 1, you can just drop the 1 in the denominator. It's just x to the 4th. So what I want you guys to look for is a really fast way to go from start to finish without having to do any of that work in the middle. So what I'm going to do is I'm going to go through the next one and do basically the same thing, and I want you guys to look for that shortcut and see if that shortcut that you found for that first one works here as well. So for b to the 7th divided by b to the 5th, what I'm going to do is I'm going to write both the numerator and the denominator as repeated multiplication. So I'm going to write the numerator as b times itself 7 times. And then I'm going to write the denominator as b times itself 5 times. Then, anytime that you have a common factor between the numerator and the denominator, they can cancel out because anything divided by itself is 1. So b over b gives you 1, b over b gives you 1, another b cancels out, and you can keep doing this until you run out of b's somewhere. So since I have run out of b's in the denominator, that means I have canceled out all of the common factors. So let's multiply what's left over. All of that all became 1. Times b, well, b times itself 2 times is b squared. And then in the denominator, all that's left over in the denominator is 1. b squared divided by 1 is just b squared. So how can we quickly go from start to finish without having to do any of that work in the middle? You might notice that you just subtract the exponents. 7 minus 5 gives you 2. And then over here, 6 minus 2 gave you 4. Now, since order matters with subtraction, what order did we subtract those exponents in? We subtracted them in the order of the top exponent minus the bottom exponent. And that's actually going to be extremely important. So that is the quotient rule for exponents. If you have two separate exponential expressions that are being divided, you can simplify by subtracting their exponents as long as they have the same base. The only reason that this worked here where we were canceling out common factors is that anything divided by itself is 1. So if you had different variables, you wouldn't be able to cancel out common factors between the numerator and denominator because they wouldn't be considered common factors. So this process only works if both the numerator and the denominator are exponentials of the same base. So if you have division of two exponentials with the same base, you can simplify by subtracting the exponents. And because order matters with subtraction, it is always the top exponent minus the bottom exponent. So if you have x to the a divided by x to the b, you can simplify by subtracting the exponents, x to the power of a minus b. top minus bottom. So what we're going to do for each of these is we are going to use the quotient rule for exponents to simplify each of these expressions. Just make sure, if possible, remember the only reason that that rule works is if the expression in the numerator and the expression in the denominator have the same base. So for 10 to the 5th divided by 10 squared, I have two exponentials of the same base 10 that are being divided. So I'm going to simplify by subtracting their exponents, top minus bottom. So 5 minus 2 will give us 3, so 10 to the 3rd is going to be fully simplified. Then for x to the 12th divided by x to the 7th, I have two exponentials of the same base x that are being divided. So I'm going to simplify by subtracting their exponents. So 12 minus 7, remember top minus bottom, gives us x to the power 5. Then for this next one over here on the bottom left, I have y to the 13th divided by y. Remember, if you ever have a variable with no exponent, you can always assume that there is a 1 there. So y to the 13th divided by y to the power 1. These are two exponentials of the same base that are being divided. So I'm going to simplify by subtracting their powers. 13 minus 1 is 12. And then for the last one, we have x to the 4th divided by y squared. Can we simplify this by subtracting their powers? And the answer is no, because the bases are not the same. When the bases are not the same, you cannot simplify this any further. The reason that you cannot simplify this any further is because the bases are not the same. That means that you wouldn't be able to cancel out common factors between the numerator and denominator like we did here, which is what you're effectively doing when you subtract the powers. So because the two bases are not the same, this expression is fully simplified and cannot simplify any further. Now, one thing that I do want to emphasize is in the quotient rule for exponents, it is always the top exponent minus the bottom exponent, even if the bottom exponent is bigger. Just please keep that in mind. Yes, you're going to have negative exponents. We're going to cover rules for negative exponents. So just keep that in mind. We're going to get to that. There is a way to deal with negative exponents. Anyways, so what we're going to do for each of these is we've covered enough of the exponent rules to be able to simplify these slightly more complicated expressions using the exponent rules. Now, product rule for exponents, because order doesn't matter for multiplication or addition, you can use product rule for exponents on as many exponentials being multiplied as you want, as long as all of the bases are the same. So x to the power 3 times x to the power of 1, remember there's a hidden 1 there, times x to the power 5. Yes, there are 3 exponentials being multiplied, but because they are all being multiplied and all of their bases are the same, that means that we can simplify it by just adding all of their power. So 3 plus 1 plus 5 gives you x to the power 9. So the product rule for exponents can expand to 3 or more exponentials all being multiplied as long as they all have the same base. Now for this next one, for a squared b times ab to the 4th, there is a whole ton of hidden multiplication here. There is hidden multiplication right there, between the two parentheses, and again right there. Now, product rule for exponents applies to when you have two exponentials that are being multiplied and their bases are the same. And order doesn't matter with multiplication. So you can switch the order of multiplication however you want. And because multiplication is also associative, that also means that you can group multiplication however you want. So I have a combination of a's and b's here. And since they're all being multiplied, you can go ahead and, put all of the a's together if you want to, and then all of the b's together. And you can do that because order doesn't matter with multiplication. Now, product rule for exponents works when you have two exponentials of the same base that are being multiplied. So for a squared times a to the power 1, I'm going to use the product rule for exponents to simplify these. So that will simplify to a cubed. You're going to add the powers. Then I'm going to multiply. I'm going to do the same thing here for b to the 1 times b to the power 4. I'm going to simplify by adding the exponents. 1 plus 4 gives us b to the 5. Now, because a and b are now different bases, this is actually fully simplified. You know that an exponential expression is fully simplified if you only have one of every base. So since we only have this a to the third and b to the fifth, you can't actually combine their exponents because they're different bases, so that would be fully simplified. Now for this last one, for any time that you have division or any sort of quotient rule for exponents or really any other division only works when you have one exponential in the numerator and one exponential in the denominator. That's because you can only divide two things at a time, one expression in the numerator and one expression in the denominator. So you might remember from when you learned order of operations in previous courses, whether that was intro algebra or some other previous course, that if you have any other operation on either the top or bottom of a fraction, you need to perform that operation first before you do any division, because you can only divide two numbers at a time. The same thing is going to apply here. We can only divide a single t to a power in the numerator by the t squared in the denominator. So before I can even think about this division, I do need to simplify the numerator. So even though there are no parentheses here, you can always imply that there are parentheses around an expression like this. So I'm going to make sure that I simplify that first before I even tackle the divided by t squared. So I'm just going to leave this over t squared alone for right now, and I'm going to simplify the numerator down to one single exponential. Now in the numerator, I have two exponentials of the same base t that are being multiplied together. So the product rule for exponents says I can simplify by adding their powers. 3 plus 5 gives you t to the 8th. Now that I have one single exponential in the numerator and one single exponential in the denominator, now I can simplify using the quotient rule for exponents. So I have two exponentials of the same base t that are being divided. So I am going to simplify by subtracting their exponents in the order of the top exponent minus the bottom exponent, which will give you t to the 6th. Also, I cannot stress enough that for quotient rule for exponents, it is always top exponent minus bottom exponent, even if the bottom exponent is bigger. Now, yes, if the bottom exponent is bigger, with quotient rule for exponents, you will end up with negative exponents. So there are going to be two different rules for negative exponents. So there's going to be a negative exponents rule part 1 and a negative exponents rule part 2. I'm going to show you why the rules for negative exponents work the way they do by once again writing these as repeated multiplication. You don't have to do this every single time, but I'm just going to show you why it works the way it does. Now, if you were to simplify this expression using the quotient rule for exponents, you would do the top exponent minus the bottom exponent, which would give you 6 to the power of negative 3. And I'm going to tell you this right now. You do not want a negative exponent on your final answer except in the context of scientific notation. But outside of the context of scientific notation, negative exponents in a final answer are not okay. They're one of those simplifying things where you need to make sure that your answer always contains positive exponents and only contains positive exponents. So there is a way to simplify this further that will make the exponent positive. And to show you what that rule is and how to do that, I'm going to take 6 to the 4th over 6 to the 7th, and I'm going to write both the top and the bottom as repeated multiplication, basically doing the same thing I did when we discovered the quotient rule for exponents. So 6 to the 4th is going to be 6 times itself 4 times. And then 6 to the 7th is going to be 6 times itself 7 times. Then any common factors that can cancel out between the top and the bottom can do so. And remember, Anything divided by itself is 1. So when they cancel out, they don't go away, they just become 1. So 6 divided by 6 is 1. 6 divided by 6 is 1. 6 over 6 is 1. And 6 over 6 is 1. So then I'm going to multiply what's left over in the numerator and what's left over in the denominator. So in the numerator, 1 times 1 times 1 times 1 is 1. Over 1 times 1 times 1 times 1 is 1. Times 6 times itself 3 times. Now, 6 times itself 3 times can be simplified to 6 to the power 3. So this expression overall will simplify down to 1 over 6 to the power 3. Now, ones in a denominator can be dropped and gotten rid of. Ones in the numerator cannot. So no, you cannot just turn this into 6 to the third power. If you have a 1 in the numerator, you do need to leave it there. So this would be how it fully simplifies. So back to how this ties in with negative exponents. If you were to use the quotient rule for exponents, you would get 6 to the power of negative 3. But as we just saw, if you wrote this as repeated multiplication, it simplifies to 1 over 6 to the third. So you can take this 6 to the power of negative 3, and you can write it as 1 over 6 to the power 3. Notice how this exponent here is a positive 3. So here's how to turn negative exponents into positive exponents. There's going to be two parts to this rule. If your negative exponent is in the numerator, so x to the power of positive a, what you will do is you will move it to the denominator and change it to a positive. Remember, the whole point of moving this exponent is to change it to a positive, so don't forget to do that. So x to the power of negative a will simplify to 1 over x to the power a. So if you have a negative exponent, you're going to move it to the denominator and change it to a positive. And remember, you never want negative exponents in a final answer, except in the context of scientific notation. So what we're going to do for each of these is we are going to use that rule for negative exponents to simplify each of these expressions. The final answer should only contain positive exponents. So 5 to the power of negative 2 would need to be simplified. So if there is no denominator, you are going to create one. And then you are going to move the base and the exponent that's negative. So I'm going to move both that negative 2 and its base 5. I am going to move them both into the denominator and change that negative 2 to a positive 2. Now, blank denominators are okay, but blank numerators are not okay. So you cannot have a blank numerator like this. What goes in the numerator would be anything that you left behind. And if you didn't leave anything behind, if there's nothing left over when you move your base and exponent, then if there's nothing left over, you put a 1 in the numerator. So 1 over 5 to the power of positive 2 would be your final answer. We're going to do the same thing to simplify x to the power of negative 8. So if there is no denominator, you are going to create one. And then you're going to move both the base and the negative exponent, both of them together. You're going to move them both into the denominator. And you're going to change the negative 8 to a positive 8. And then if you did not leave anything behind, which we didn't, you put a 1 in the numerator. So if there's nothing left over, there's a 1 in the numerator. Now, when your exponential contains parentheses, where the parentheses are and what the parentheses are wrapped around makes a huge difference. So for this next expression here, the exponent is negative 1. The base of that exponent is whatever is to its immediate left. And if to its immediate left you have parentheses, that means that everything in the parentheses and only what's in the parentheses is being raised to the power of negative 1. So since the parentheses end right here, the negative is not inside the parentheses, and that is extremely important. That means that this negative is not part of the exponential and is considered separate. So the exponential is only this parentheses 8x to the power of negative 1. And since the exponent is negative, you are going to have to simplify it to turn it into a positive exponent. So if there is no denominator, which there isn't, I'm going to create one. And I'm going to move only the negative exponent and its base into the denominator. So this 8x to the power of negative 1, that is what is getting moved into the denominator, and that will become 8x to the power of positive 1. Now you might notice I left this negative behind. Anything that you leave behind goes in the numerator, and if you have a negative just in front of parentheses like that, you can always assume that there's a 1 there. So there is a negative 1 left over in the numerator. And then 8x to the power 1, you don't really need that power of positive 1 because anything raised to the power 1 is itself. So negative 1 over 8x would be your fully simplified final answer. So then for this last one, again, the base of an exponent is only what's to its immediate left. And if there are parentheses to its immediate left, that means everything in parentheses is considered the base of the exponential. So the base of this exponent of negative 2 would be this parenthesis negative 4. And because the parentheses, the negative is in the parentheses, that means the negative is also being raised to the power of negative 2, and that means the negative is part of the exponential. So since the negative exponent is since the exponent is negative, we are going to have to simplify it. Since there is no denominator, I am going to create one. And then I am going to take both the base and the negative exponent, parentheses and all. I am going to move them all into the denominator. Again, if the parentheses are there to begin with, they do need to stay there. And then I'm going to turn that negative 2 into a positive 2. Sorry. I'm going to turn that negative 2 into a positive 2. Now, the only thing that changes signs are the exponents. If your base was negative, that negative 4 stays negative. It's the exponent that changes signs. So that exponent of negative 2 will turn into an exponent of positive 2. Now, since I did not leave anything behind, if you have nothing left over, there is a 1 in the numerator. So for each of these, I can't stress enough that the base of an exponential is only what's to its immediate left. And if there are no parentheses to group, let's say 8 and x together, or the negative and the 4 together, then they're not going to be grouped together. So for this next one, this 2 to the negative 1q, remember there is hidden multiplication right here. So because there is hidden multiplication here, you have to remember order of operations. Exponents always take priority over multiplication. So another thing is that the only thing that you ever need to move into denominators like this are negative exponents. Anything that has a positive exponent doesn't need to go anywhere. It doesn't need to move anywhere because if its exponent is already positive, you don't have to worry about it. So for this q to the negative 1, this 2 to the negative 1 times q, the q has an exponent of positive 1. So because of that, q doesn't need to go anywhere. We don't need to do anything with q. The only thing that would need to move is this 2 to the power of negative 1. So what I'm going to do is if I don't see a denominator, I am going to create one. I am only going to move the base and the negative exponent into the denominator. So this 2 to the negative 1 is all that is going to get moved into the denominator to become 2 to the positive 1. Now, this q to the power of 1, this 1 was already positive. Don't move it. Don't move anything that already has a positive exponent. So since this didn't need to move, I effectively left it behind. So since I left q behind, q goes in the numerator. Anything that you leave behind goes in the numerator. So q over 2, because 2 to the power of 1 is itself, is going to be your final answer here. Now for this next one, for this 5x to the power of negative 2, notice that there are no parentheses around the 5 and the x, and that is actually extremely important. Because without parentheses, the 5 and the x are not being grouped together. And remember, there is also hidden multiplication between this 5 and this x. So just like with that last one, exponents always come before multiplication. And because there are no parentheses around the 5 and the x, that means the base of this exponent of negative 2 is just x, Without parentheses, the 5 is not part of this exponential because the multiplication is considered separate. So, because this exponent is negative, I am going to have to simplify it, and since there is no denominator, I am going to make my own denominator. And the only thing that needs to get moved into the denominator is the negative exponent and the base that goes with it. So the base of that exponent of negative 2 is just x. So just that x and its exponent move into the denominator to become x to the power of positive 2. And then what did I leave behind? Well, this 5 had a power of positive 1. So because the exponent on 5 was already positive, you don't need to move it. You don't need to do anything with it. So since I left 5 behind, 5 goes in the numerator. So 5 over x squared would be your fully simplified final answer. Now, negative exponents are going to be something that crops up a lot when you are simplifying other exponential expressions using other exponent rules, especially the exponent rule with quotients, the quotient rule for exponents. So for something like y to the 6th divided by y to the 10th, you would notice that we have two exponentials of the same base that are being divided. So we are going to use the quotient rule for exponents to simplify. And we're going to simplify by subtracting their powers. Now remember, the order of the subtraction is always the top exponent minus the bottom exponent. So 6 minus 10 is y to the power of negative 4. And no, you do not want to leave your answer like this. Your final answer should only contain positive exponents. So since this is y to the power of negative 4, we need to simplify a little bit further. So I no longer have a denominator because when you use the quotient rule for exponents, you effectively get rid of it. So I'm going to create a new denominator. I'm going to move y to the power of negative 4 into that denominator to become y to the power of positive 4. And since I didn't leave anything behind, there is a 1 in the numerator. So 1 over y to the 4th is our final answer. Now, because this business of moving exponents into denominators, it can get a little cumbersome sometimes. You don't have to, but I would highly recommend that you move negative exponents as a last step before your final answer. So if you have any other exponent rules, I would personally recommend that you do all of those first and then move negative exponents kind of at the end as your last step before you're ready to call it good and call it your final answer. So for this next one, yes, at first glance, we've got a lot of negative exponents. They're going to need to move. But you might notice that we have other exponent rules at work here. We have this x to the power of negative 5 times x to the power of 2. Let's simplify those two first before we even really worry about any negative exponents. So I'm just going to leave that 4 to the power of negative 1 alone for right now. I'm going to leave the times alone for right now. And I'm going to simplify x to the negative 5 times x to the power 2. So I have two exponentials of the same base that are being multiplied. That means I'm going to use the product rule for exponents. Product rule for exponents says that you can simplify by adding the powers. So negative 5 plus 2 is x to the power of negative 3. So now that we have just one of every base, we have this base of 4, this base of x. We can't actually combine these any further because their bases are not the same. So now I'm going to worry about the negative exponents. So since I do not have a denominator, I am going to create one. Anything with a negative exponent needs to move into that denominator. So this x to the power 3 has a negative exponent. It's going to get moved into the denominator to become x to the power of positive 3. And the same thing for this 4 to the power of negative 1. Since this has a negative exponent, it too is going to move into the denominator to become 4 to the power of positive 1. And if you don't leave anything behind, there is a 1 in the numerator. So if there's nothing left over, there is a 1 in the numerator. And then just real quick, 4 to the power 1 is itself, so you can just write this as 1 over 4x cubed. And then that's a nice, clean, condensed final answer. Now, I did say that there was a part 2 to the negative exponents rule, and that applies when your negative exponent is already in the denominator. So if you have a negative exponent in the denominator, what you're going to do is you're going to move it to the numerator to make it positive. So basically with negative exponents, you are going to move it to the other part of the fraction to make it positive. If your negative exponent's in the numerator, you move it to the denominator. If your negative exponent's in the denominator, you move it to the numerator. So 1 over x to the power of negative a will be x to the power of positive a. So you just move your negative exponent to the other part of the fraction to make it positive. So what we're going to do is we're going to simplify each of these, making sure that our expression only contains positive exponents. So for this 5 over x to the power of negative 4, 5 and x are different bases, so we can't actually use the quotient rule for exponents here. But you will notice that this x to the power of negative 4, it's negative. So since our final answer should only contain positive exponents, I'm going to need to deal with this. Now, since your power of negative 4 is already in the denominator, what we're going to do to make it positive is we're going to move it to the numerator. So I'm going to move this x to the power of negative 4 to the numerator to become x to the power of positive 4. Now, if you don't leave anything behind in the denominator, there is technically a 1 in the denominator. And 1s in the denominator aren't necessary. 1s in the numerator, yes, are absolutely necessary. But if you have a 1 in the denominator, you can just get rid of it, because 5x to the 4th divided by 1 is just itself 5x to the 4th. So blank denominators are okay. If you have a 1 in the denominator, you can go ahead and get rid of it. But just remember, you can't do that for 1s in the numerator. Now for this next one, for 1 over 3y to the negative 1, notice how there are no parentheses around the 3 and the y. Remember, if there are no parentheses around the 3 and the y, that means 3 and y are not grouped together and they are considered separate. There is hidden multiplication between this 3 and this y. And since exponents always come before multiplication, the only thing that is being raised to the power of negative 1 is this y, and that 3 is not included. So what I'm going to do is, because this exponent is negative, I'm going to need to move it to become positive. And since y to the negative 1 is in the denominator, what I'm going to do is I'm going to move it to the numerator to become y to the power of positive 1. And this 1, was just still there. Now, I did leave something behind. I did leave that 3 behind. And since that 3 contained an exponent of positive 1, it did not need to move. So that 3 was left over in the denominator, and then, y to the power 1 is itself over 3. So y over 3 is your fully simplified final answer. And then we're going to do the same thing for this last one. So for a squared divided by b to the negative 3, a and b are completely different bases, so we can't actually simplify them using quotient rule for exponents. But what we can do to make sure that our answer only contains positive exponents. So because this b to the power of negative 3 is already in the denominator, what I'm going to do is I'm going to move it to the numerator to become positive. So the a squared, I'm just going to leave it where it is, and I'm going to move this b to the negative 3 into the numerator to become b to the positive 3. And remember, if you leave nothing behind, there is a 1 left over. 1's in the denominator you can get rid of. So we can just write this as a squared times b to the 3rd, and then that will be your final answer. I'm sorry about what just happened there. My stylus it does glitch out sometimes, so that will just happen, and it's outside of my control, and nothing I've ever done has been able to fix it. So I'm sorry in advance for things like that happen. There's nothing I can do about it. I'm sorry. Anyways, so more exponent rules that we are going to cover is, one of them is raising a product to a power. Now you might notice, for this, like that 3y in that last example, there were no parentheses around the 3 and the y. But if there were, that would mean that everything in the parentheses is being raised to that outside power. And there is a way to simplify products that are being raised to outside powers. So if you have 5x to the power 3, again, the parentheses are grouping together the 5 and the x. So what the parentheses mean is that both the 5 and the x are both being raised to this outside power 3. So because there is hidden multiplication here, you can kind of think of these as separate. So what I'm going to do is I'm going to write this as repeated multiplication. I'm going to show you where this rule comes from and why it works the way it does, and then hopefully that will allow you to remember it and then remember how to use it. So I am going to actually write this as 5x times itself 3 times. Now, because order doesn't matter with multiplication, and you can group multiplication however you want, this is just one giant string of multiplication. So because of that, what I'm going to do is I'm going to simplify by simply combining the repeated multiplications of the same base into their one exponential, and then repeated multiplication of another base as another exponential. For example, I have this 5 here. How many times in total have I multiplied 5 by itself? Well, I've multiplied 5 by itself 3 times. So I'm going to write that as 5 to the third. Then I have this other base x. And in total, how many times have I multiplied x by itself? Well, I've multiplied x by itself 3 times, so I'm going to write that as x to the third. So you can rewrite that 5 times x parentheses to the third power as 5 to the third power times x to the third power. So that's the gist of how to raise a product to a power. You can simply take each part of that product and raise it to the outside power. So if you have x times y parentheses to the power a, you can simply take the first part of the product x, raise it to the outside power a, and then multiply it by the other part of the product y, raised to the outside power a. So in other words, if you're raising a product to a power, you can raise each part of that product to that outside power. And the key is there need to be parentheses there, because the parentheses will group that product together. If you do not see parentheses, that means that not every part of that product is being raised to that power. So pay very close attention to where the parentheses are. So you can distribute a power across multiplication, but you cannot, under any circumstances, distribute a power across a plus sign or a minus sign. So for example, x plus y to the power a cannot be written as x to the power a plus y to the power a. Same thing with subtraction. You cannot write x minus y to the power a as x to the power a minus y to the power a. So because they're too far removed in order of operations, you cannot distribute a power across a plus sign or a minus sign. But you can do that across multiplication. So we're going to use that raising products to powers rule to simplify each of these. Now pay attention to where the parentheses are, because the parentheses will indicate what is being raised to that outside power. So for this first one, we have 2 times y parentheses raised to the power 4. Because the parentheses are around both the 2 and the y, and the 4 is outside the parentheses, that means the 2 is being raised to the power 4, and the y is being raised to the power 4. So that's how I'm going to write it. I'm going to write this as 2 to the outside power 4 times y to the outside power 4. Now for this next one, for the one on the top right here, notice how the negative is in parentheses. And especially with negatives, if the negative is in the parentheses to begin with, it does need to stay in parentheses even after you simplify using these rules. So for negative 3 times a, all raised to the outside power 2. What we're going to do is we're going to raise each part of this product to that outside power 2. So I'm going to take negative 3, and because the negative was in the parentheses, I'm going to leave it in the parentheses. I'm going to raise it to the outside power 2. And then I'm going to take this a, and then I'm going to raise it to the power 2. And the reason why it's important that if the negative is in parentheses, it needs to stay in parentheses, is because when the negative is in parentheses, that means both the negative and the 3 are both being squared. So this is the same as negative 3 times negative 3, which is positive 9a squared. Now, if the negative is not in the parentheses, like this next one, that would imply that there is a negative 1 that is being multiplied here. And you might remember from order of operations that exponents always come before multiplication. So what's happening here is as soon as the parentheses end, the exponential ends. So only this positive 3 and the a are being raised to the power 2, and that negative is technically a separate negative 1 that is being multiplied. So this 2 would only go to the 3 and the a. So this would be 3 squared times a squared. And since exponents come before multiplication, the only thing being squared here is this positive 3, which is 9, but the negative 1 would be considered separate, so this would simplify down to negative 9a to the power 2. So pay very close attention to what is in the parentheses, especially with negatives. If the negative is in the parentheses, that means it too gets raised to that outside power. If the negative is not in the parentheses, it is not raised to the outside power and it is considered separate. So we're going to basically do the same thing for this next group. Now, if any of the parts of the product in the parentheses have existing exponents, then the power rule for exponents is going to kick in when you raise a power to another power. So for example, for 2 times x to the 4th, because all of this, including the x to the 4th, is in parentheses, all of that is being raised to this outside power 5. So what I'm going to do first is I'm going to use the raising a product to a power rule to raise each part of this product to that outside power 5. So I'm going to take the first part of the product 2, going to raise it to the outside power 5. Then I'm going to multiply it by the second part of the product, which is x to the 4th. Notice I kept the parentheses. And I'm going to raise x to the 4th to the outside power 5. So if you look at this over here, this x to the 4th raised to the power of 5, we have a power raised to another power. So according to the power rule for exponents, we can simplify this by multiplying the power. So 4 times 5 will give us x to the power 20. So we're going to do the same thing for this next one. Because the parentheses are around all of this, that means this entire product, this p to the 3rd times q to the 5th, is all being raised to the outside power 3. So I'm going to raise each part of that product to that outside power first. So I'm going to take p to the 3rd, I'm going to leave parentheses around it for now, and I'm going to raise it to the outside power 3. Then I'm going to multiply it by q to the 5th, and again I'm going to leave the parentheses there for right now, and I'm going to raise it to the outside power 3. Then anytime that you have a power raised to another power, you can simplify it by multiplying the powers. So 3 times 3 will give us p to the power 9. And then times 5 times 3 will give us q to the power of 15. And because p and q are different bases, that means this is fully simplified. So fully simplified, we have p to the 9th times q to the 15th. Now, anything not in parentheses is not raised to the outside power because, remember, exponents always come before multiplication. So for this next one, this negative 7, which is being multiplied by the parentheses, is not considered part of this exponential here. As soon as the parentheses end, the exponential ends. So the only thing that is being raised to the power 2 is this m to the 5th times n to the 10th. That negative 7, which is being multiplied outside the parentheses, is considered separate, and it does need to remain separate. So I'm just going to leave that negative 7 where it is. And then I am going to simplify the exponential by taking each part of this product and raising it to the outside power 2. So I'm going to take m to the 5th with parentheses around it, and I'm going to raise it to the outside power 2. Then times, I'm going to take n to the 10th with parentheses around it and raise it to the outside power 2. And then any time that you have a power raised to another power, you can simplify by multiplying the powers. So 5 times 2 will give us m to the 10th. And then 10 times 2 will give us n to the 20th. And because these are all different bases, including that negative 7, this is going to be your fully simplified final answer. You know that you're done when you only have one of every base and all of your exponents are positive. You don't have any negative exponents. So you're done when you have only one of every base and all of your powers are positive. And like I suggested, I would highly recommend that you move negative exponents kind of as a last step. So for this next one, even though there's a ton of negative exponents here, I'm just going to work with it for now. I'm going to use any and all other exponent rules first. And then once I have finished every single other exponent rule that I possibly can, then as a last step, I'm going to move negative exponents around. So I have 3 parts of this product in parentheses. So it means everything in the parentheses is all being raised to this outside power -2. So all 3 parts of this product are all getting raised to that outside power. So I'm going to take each part of this product and raise them all to the outside power -2. So I'm going to take this 5 and raise it to the power of -2. Again, I guess the parentheses weren't really necessary there. Then I'm going to take this a to the -2, which does need parentheses, and I'm going to raise it to the outside power of -2. Then I'm going to take that c to the 4th, which needs parentheses around it, and I'm going to raise it to the outside power -2. Anytime that you have a power raised to another power, you can simplify by multiplying the powers. So I have this 5 to the power of -2 times, for this a, -2 times -2 is a to the power of +4. So that's partly why we do the negative exponent thing as a last step. And then for 4 times -2, that gives us c to the power of -8. So as you can imagine, that's kind of why we move negative exponents kind of as a last step, because if you're multiplying exponents especially, you might get some negatives times negatives giving you positives and positives times negatives giving you negatives. So now that we have exhausted all other exponent rules and we're down to just one of every base, now I'm going to worry about the negative exponents. So since I do not have a fraction, I am going to create one. Anything with a negative exponent needs to move into the denominator. Anything with a positive exponent needs to stay where it is. So this c to the power of -8, because the exponent is negative, it needs to move into the denominator to become c to the power of +8. Now this a to the 4th, this was a power of +4. Because of that, we don't need to touch a to the 4th. This doesn't need to go anywhere, so please don't move it. Actually, moving it would make it worse, so just don't move a to the 4th. However, this 5 to the power of -2 does need to move, so this 5 to the power of -2 will move into the denominator to become 5 to the power of +2. Now that a to the 4th that you did not move or didn't need to move was left behind. Anything that is left behind goes in the numerator. So that a to the 4th that I left behind will go in the numerator. So your fully simplified final answer would be a to the 4th over 5 squared c to the 8th. And then another rule for exponents is when you raise a quotient to a power. You're going to be using this rule anytime that you, like, say, square a fraction, like taking 1/2, let's say, and squaring it. So you're going to use this rule all the time, especially when you have any sort of fractions that's being raised to a power. So what I'm going to do is I'm going to show you where the rule comes from first. This way, hopefully you understand why the rule works the way it does and you can use it effectively. So just to show you why this rule works, I'm going to first write this as repeated multiplication. Remember, if you have parentheses and an exponent outside the parentheses, what that means is that everything in the parentheses is being raised to that outside power. That also means that everything in the parentheses is being multiplied by itself 4 times. So I'm going to write this as a over b times itself 4 times. Then, if you remember when you learned how to multiply fractions, you multiply fractions by multiplying the numerators and multiplying the denominators. So if you multiply the numerators, we have a times a times a times a. Well, I can write a times itself 4 times as a to the 4th power. Then when we multiply the denominators, b times b times b times b, well, I can write b times itself 4 times as b to the 4th. So that is how this would simplify. So basically, if you raise a quotient to a power, you can simply raise the top and the bottom to that outside power. The key is the parentheses. The parentheses indicate that the entire quotient is being raised to that outside power. If you do not see parentheses there, that means only the numerator would be raised to that power. But if there are parentheses around your fraction and you're raising it to some power a, you just take the numerator x, raise it to the power a. Then you take the denominator y and raise it to the power a. So if you raise a quotient to a power, you're going to raise both the top and the bottom to that power. That's how you can do things like square fractions. So let's say if you were doing 1/2 squared, you would just take the numerator 1, square it, take the denominator 2, square it, gives you 1/4. So that's how you raise fractions to powers. You just take the top number, raise it to that power, take the bottom number, raise it to that power. So you can distribute a power across division and multiplication. But once again, you cannot distribute a power across a plus sign or a minus sign. So what we're going to do for each of these is we are going to simplify each of them and making sure that our answer only contains positive exponents. So for x over 5 to the third, because there is parentheses around the x over 5, that means both the x and the numerator and the 5 in the denominator are both being raised to the third power. So what I'm going to do is I'm going to take the numerator x, raise it to the third power, and then I'm going to take the denominator 5 and raise it to the outside power 3. Because these are different bases, we can't simplify any more than that. Now we're going to do basically the same thing here. We have this negative a over b, and notice how the parentheses are around this entire thing. And all of that is being raised to the outside power 4. Now, I've said it several times, when you have negatives involved with exponents, if the negative is in parentheses to start with, you need to keep it in parentheses even after using exponent rules. So since this negative a was already in parentheses, it needs to stay in parentheses even when you take the numerator and raise it to the outside power 4. Then we're going to take the denominator and raise it to the outside power 4. And there is actually a way to simplify this further. If you were to take this negative a and multiply it by itself 4 times, it would look something like this. Now, a to the 4th is just a to the 4th, but look what happens when you have an even number of negatives. A negative times a negative is a positive, times a negative is a negative, times another negative is a positive. So this negative a to the power of positive 4, because you have an even number of negatives that are being multiplied, the product of an even number of negatives is positive. So this negative a to the power 4th can actually be simplified as positive a to the power 4th, because a negative raised to an even power is always positive, because an even number of negatives always multiplies to a positive. So fully simplified, this would be positive a to the 4th over b to the 4th. And then for this last one, yes, I have some negative exponents, but I'm going to exhaust all other exponents rules first before I go moving negative exponents around. So I am going to take both, since the 5 and the x are both in parentheses, what I'm going to do is I'm going to take both the 5 in the numerator and the x in the denominator and raise them both to the outside power 3. So I'm going to take 5, raise it to the power of negative 3, and then x, raise it to the power of negative 3. And now if you notice, we've got a bunch of negative exponents, so we've got a whole ton of moving around to do. So this 5 to the power of negative 3, which is currently in the numerator, can move into the denominator to become 5 to the power of positive 3. Now this x to the power of negative 3, which was already in the denominator, needs to move to the numerator to become x to the power of positive 3. And now that all of your exponents are positive and you will only have one of every base, now this is your fully simplified final answer. So if you might notice, when you have a fraction that's being raised to some sort of negative power, you might notice that it just reciprocated it. So another way you could have done this is just reciprocating it. Take its reciprocal and change the power to a positive 3, then raise the numerator to the outside power and the denominator to the outside power. Whichever way, it doesn't really matter. You arrive at the same answer regardless. There's just a little shortcut that you can use if you picked up on that and you want to use it. Now that is pretty much all of the different exponent rules that really exist. Now when you have expressions that involve multiple exponent rules at a time, I would kind of recommend, I mean, you can do a lot of these in a different order and do these slightly differently than I might do and still arrive at the same final answer. So just keep in mind that it is possible to do one of these problems in a slightly different way and still arrive at the same answer. One thing I will say though, as just a couple of points of recommendation, I would first make sure that before you do any division, like when you have quotient rule for exponents, make sure that you're only dividing two things at a time. So make sure that if you have multiples of the same base on both the top or bottom, you combine those first before you tackle quotient rule for exponents. Another thing I would recommend is before you go moving negative exponents around is you exhaust any and all other exponent rules. But again, those are just suggestions. You can still do it slightly differently and still get the same final answer. Another thing I would also recommend is if you see parentheses, try to simplify what's in the parentheses first, because in order of operations, parentheses always go first, before you really start looking at anything that is not in the parentheses. So with that in mind, let's simplify this first one. Now, I see parentheses, so I'm going to take a look inside the parentheses and see if there's anything that I can do to simplify it. So I have negative 3 times r squared, and then on the bottom I have s to the power 1 times t to the power 4. Unfortunately, inside the parentheses, we only have one of every base. We have negative 3, we have r, s, and t. So since all of the bases are different, there's really nothing to do, for simplifying inside the parentheses. But since the parentheses are being raised to the outside power 3, I am going to use a combination of raising a quotient to a power and raising a product to a power. So what I'm going to do is I'm going to take every single base on both the top and the bottom, and I am going to raise all of them to the outside power of 3. Now, if any negatives, like this negative 3 right here, are already in parentheses to begin with, they need to stay in parentheses even after you fully simplify. So I'm going to take every single base on both the top and the bottom, and I'm going to raise them all to the outside power 3. So here we go. I'm going to take negative 3 with parentheses around it, raise it to the outside power 3. Then times, I'm going to take r squared with parentheses around it, raise it to the outside power 3. Then on the bottom, I'm going to take s to the power 1, raise it to the power 3. Then I'm going to take t to the 4th with parentheses around it and raise it to the outside power 3. Now with the negative 3 to the 3rd power, you can actually evaluate this. So a negative times a negative times a negative, the product of an odd number of negatives is negative. So negative 3 to the 3rd power is actually negative 27. Then, for the rest of these, anytime that you have a power raised to another power, you can simplify by multiplying the powers. So for r, we're going to take these, we have a power raised to another power. I'm going to multiply the powers, gives us r to the 6th. Then in the denominator, for s, I have a power raised to another power, so I'm going to multiply the powers. This will be s to the 3rd. And then I have this t, so 4 times 3 will give us t to the 12th. Now let's just check, do we only have one of every base? Yes, we only have one of every base. And all of the exponents are positive. I really don't care if that 27 is negative, that's not an exponent, that doesn't matter. All of your powers are positive, that's what matters. So because all of our powers are positive, and we only have one of every base, this is now fully simplified. So I want you guys to actually try it for yourself. If you haven't tried any of these yet for yourself, I want you to start with this next one. So I want you guys to use that same kind of idea to simplify this next one. As a suggestion, you could wait to move negative exponents until the end, but that is only a suggestion. So go ahead and pause the video, try this next one, and then resume your video when you are done working and ready to check your answer. Okay, so for this next one, we have multiplication between the 9 and the u, and this entire fraction is all being raised to the outside power 2. So because in the parentheses we have all different bases, that means that there's nothing to simplify in the parentheses. So what I'm going to do is I'm just going to jump to the outside exponent 2. So I'm going to take every single thing, every single base on both the top and the bottom, and I'm going to raise them all to the outside power 2. So I'm going to take 9, raise it to the outside power 2. Then I'm going to take this u to the 1 and raise it to the outside power 2. Then I'm going to take this v to the negative 1 in the denominator and raise it to the outside power 2. Then 9 squared is 81. And then whenever we have a power raised to another power, we can simplify by multiplying the power, So for u, I have 1 times 2 gives us 2. Then in the denominator for v, negative 1 times positive 2 is v to the power of negative 2. Then, before we call this our final answer, your final answer should only contain positive exponents. So this v to the negative 2, which is currently in the denominator, needs to move into the numerator to become positive. So this will become 81 times u to the power 2 times v to the power of negative 2. And when there's nothing left over in the denominator, you can go ahead and get rid of it. Remember, blank denominators are perfectly fine and okay. Blank numerators are never okay. So if there's nothing left in the denominator, you can go ahead and get rid of it. Sorry, that is v to the power of positive 2. Sorry about that. So this is 81 u to the power of positive 2 times v to the power of positive 2. Now for this next one, again, as soon as you see parentheses or brackets, they're really the same thing. You should always see if there's any simplifying that you can do inside the parentheses or brackets first, because parentheses, in order of operations, always go first. So in the brackets here, I have 6x squared y to the third over 8x to the seventh y squared. So you might notice that we have more than one of a couple of the bases. We have an x on the top here and an x on the bottom here, and a y on the top here and a y on the bottom here. So let's simplify that first before we tackle this outside power of negative 3. So I am going to fully simplify what's inside the brackets first before I go tackling that outside exponent. So one thing that we can do with this is 6 over 8. 6 and 8 have a common factor of 2, so let's go ahead and reduce 6 over 8. So 6 divided by 2 is 3, 8 divided by 2 is 4. Let's go ahead and simplify that to 3/4. Then what I'm going to do is I'm going to combine the x's and the y's, and since we have division here, we're going to use the quotient rule for exponents because we have the exponential x to the power of 2 divided by x to the power of 7. Now, what I would recommend is do the subtraction first, and as soon as you subtract, move them to the numerator. So we're going to subtract, and as soon as we're done subtracting, we'll move it automatically into the numerator, and if we need to move any exponents that are negative, we will do that later. So top exponent 2 minus bottom exponent 7 gives us x to the power of negative 5, and I'm just going to put it in the numerator for now. I'll move it later. Then I'm going to do the same thing for the y. So I have y to the power 3 divided by y to the power 2. Because I have two exponentials of the same base that are being divided, I am going to simplify using the quotient rule for exponents. So I'm going to subtract the exponents. Top minus bottom is y to the power of 1. And then I'm going to raise that all to the outside power, negative 3. And there are a bunch of different ways that you can tackle this. I'm only going to do it one way, but just keep in mind that if you're trying this on your own, you can do this in, I can think of at least 2 different ways and still arrive at the same final answer. So even if your work looks different, if you get the same final answer that I do, that means you did it correctly and you're completely fine. You don't need to email me in a panic thinking you did it wrong. If you arrive at the same answer and you're using all the same exponent rules, just maybe in a different order, you're fine. So what I'm going to do is, now that inside the brackets we only have one of every base, now I am going to take every single base on both the top and the bottom, and I'm going to raise them all to that outside power -3. So I'm going to take this 3, and I'm going to raise it to the power of -3. Then I'm going to take this x to the power of -5 with parentheses around it, and I'm going to raise it to the outside power -3. Then I'm going to take this y to the power 1 with parentheses around it, and I'm going to raise it to the outside power -3. Then don't forget there was a denominator. I'm going to take that 4 in the denominator and raise it to the outside power -3. And then anytime that we have a power raised to another power, we're going to simplify by multiplying the powers. So I have 3 to the -3, which I'll deal with in a minute. Then for this x, -5 times -3 is +15. Then +1 times -3 is y to the power of -3. And don't forget that was all divided by 4 to the power of -3. Now that we have one of every base and we've pretty much exhausted all other exponent rules, now I'm going to worry about moving negative exponents around. So any negative exponent needs to move to the other part of the fraction to become positive. And remember, anything that already has a positive exponent can stay exactly where it is. So this 3 to the power of -3 is going to move into the denominator to become 3 to the power of +3. X to the power 15. Since this 15 is positive, we can just leave it alone. We're going to leave it in the numerator. Then this y to the power of -3 needs to move into the denominator to become y to the power of +3. And this 4 to the power of -3, which was already in the denominator, needs to move into the numerator to become 4 to the power of +3. And then if you want, you can leave it like this, or you can simplify, 4 to the third is 64, 3 to the third is 27, whichever. But as long as there is only one of every base and all of your exponents are positive, that means that this is your final answer and you are all set with using exponent rules. So then for this next one, keep in mind that these brackets, notice how these brackets went over the entire fraction? That meant that the entire fraction was being raised to that single outside power -3. For this next one, the numerator and denominator have their own sets of parentheses. So because of that, the entire fraction is not being raised to the same power. These parentheses indicate that only what's in the numerator is being raised to the power of -3. And these parentheses here indicate that only what is in the denominator is being raised to the power 2. So when we raise each base to that power, as soon as the parentheses stop, that exponent stops. So for example, I'm going to take only what's in this numerator here, only what's in these parentheses, and I am going to raise them to that outside power -3. So I'm going to take 2, raise it to the power of -3. I'm going to take r squared with parentheses around it and raise it to the power of -3. Then I'm going to take t to the power -1 and raise it to the power of -3. And as soon as those parentheses stop, that means we're done with that exponent of -3. We're not going to raise everything on the bottom to the -3. What we are going to do is we're going to take each of these bases on the bottom and we're going to raise them to the outside power 2. So I'm going to take r to the -3, raise it to the outside power 2. Then I'm going to take the t to the 4th, and raise it to the outside power 2. Anytime that you have a power raised to another power, you're going to simplify by multiplying the powers. And again, I'll deal with the negative exponents later. For r here, I have positive 2 times -3 is r to the power of -6. And then for t, -1 times -3 is t to the power of +3. Then in the denominator, -3 times +2 is r to the power of -6. And then 4 times 2 gives us t to the power 8. Now, before we start moving negative exponents around, you might notice that we now have more than one of every base. So now that the parentheses are done and the outside powers are done, now we need to start thinking of, oh hey, I have r to the negative 6 divided by r to the negative 6. Let's simplify that because these are the same base. Now, you can do this in one of two ways. You can either think of this as r to the negative 6 divided by itself, or you can use quotient rule for exponents, top exponent negative 6 minus negative 6. You might notice that anything divided by itself is 1, or that r to the power 0 is equal to 1. So basically, the r to the negative 6 on the top and the bottom can cancel out and become 1 because anything divided by itself is 1 and anything raised to the power 0 is 1. Now this 2 to the negative 3 is not going to combine with anything, so I'm just going to leave it alone. But these t's here can combine because we have a t to the third on the top divided by t to the eighth on the bottom. So we have two exponentials with the same base that are being divided. So I'm going to simplify by subtracting their exponents. Top exponent minus bottom exponent gives us t to the negative 5. And as a suggestion, when you use quotient rule like this, when you subtract your exponents, put it on the top first, and if it's negative and you need to move it, then move it later. So when you subtract, just automatically put it in the numerator, move it if you need to. So now what I'm going to do is, now that I only have one of every base, 2 and t are now different bases, now I'm going to start worrying about negative exponents. So I'm going to take this 2 to the power of negative 3. Since it's in the numerator, I'm going to move it to the denominator to become 2 to the power of positive 3. And since I put this t to the negative 5 in the numerator to start with, and it's negative, I'm going to move it to the denominator now to become t to the power of positive 5. And we did not leave anything behind. There was nothing left over after we moved those two. So if there is nothing left over in the numerator, you need to put a 1 in the numerator. You cannot leave a numerator blank. So 1 over 2 to the third t to the fifth is your final answer. Or you can write this as 1 over 8 t to the fifth, whichever. So that is basically the general gist of how to simplify expressions that involve exponents. Now this slide, which this entire PowerPoint, including this slide, is posted on Canvas, so you can, if you want to print off this slide to kind of have a reference sheet, just go on Canvas and find it, and you're more than welcome to print this out. But this is just kind of a general one-stop shop for all of your exponent rules. Anything raised to the power 1 is itself. Anything raised to the power 0 is 1. If you have two exponentials that are being multiplied together, you can add their powers. If you have two exponentials of the same base that are being divided, you are going to subtract their powers. If you have a negative exponent, you are going to move that negative exponent to the other part of the fraction to become positive. If you have a power raised to another power, you're going to simplify by multiplying the powers. If you have a product raised to a power, you're going to raise each part of that product to that outside power. And if you have a quotient raised to a power, you're going to raise both the top and the bottom to that outside power. Now remember, when you're simplifying these, you know when you're done if you only have one of every base and your answer only contains positive exponents. Your final answer should only contain positive exponents. The only time when negative exponents are acceptable and needed in a final answer is in the context of scientific notation. And speaking of scientific notation, we are going to go through this a little bit because scientific notation is one of the major applications of integer exponents. So what scientific notation is it is a more condensed way of writing either very large numbers or very small numbers. And the way that it condenses these very large or very small numbers is it uses powers of 10 to represent the place values or the decimal places. So let's say that your number contains a lot of digits, such as this very large number or this very small number. These can be written in scientific notation by using powers of 10 to represent each of these decimal places. So how it works is a number that is in scientific notation is always written in the form of a times 10 to the power n, where n is some integer exponent. Integers are positive and negative whole numbers, so n is going to be some positive or negative whole number exponent. And this number a in front is any number between 1 and 10, usually a decimal, but not always. But a is some number between 1 and 10. The smallest that a could be is 1, but a could be 9.999, but a has to be smaller than 10 because as soon as a equals 10, you've got another power of 10 here. So a is somewhere between 1 and 10. Now, large numbers use positive powers of 10. So a times 10 to a positive power would indicate a very large number. Small numbers use negative powers of 10. So a times 10 to the power of negative n would be a small number. So this form right here, this a times 10 to the power n, is called scientific notation. Now, if you were to write out the number with all of the zeros, like this or like this, that is what is called standard form or decimal form. So if you want to take a number that is already written in scientific notation and write it in decimal form, all you have to do is move the decimal point either to the right or to the left as many places as the power of 10. Now, if the power is positive, that indicates a large number, so you're going to move it to the right that many places. If the power is negative, that indicates a small number, so you're going to move your decimal point to the left that number of places, and you'll move it as many places as there are powers of 10. So for example, let's say that we have this number here. It is currently in scientific notation, and we're going to write it in standard or decimal form. Decimal form would be the form with all the zeros. So what we're going to do first is we're going to figure out whether this is a large number or a small number, and we're going to do that by looking at the power of 10. This power of 10 is a positive number. So because it's positive, that means we have a large number. So what I'm going to do is I am going to kind of take my number as is for right now, 3.9785. I'm going to locate the decimal point, and I am going to move that decimal point as many places as there are powers of 10. And since this is a positive exponent, that indicates a large number. So I am going to move this decimal point to the right 10 places to turn this number into standard form. So I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my decimal point has landed right there, and then in all of those gaps, we are going to put 0. So we're going to have a 0 here, 0, 0, 0, 0, 0. So written in standard form or decimal form, it looks something like this: 3, 9, 7, 8, 5, and 1, 2, 3, 4, 5, 6 zeros. Like I said, scientific notation is a way of writing really large numbers or really small numbers in a more condensed format. Now for the next one, for 6.8 times 10 to the negative 9, because your exponent is negative, this indicates a very small number, a very small decimal. So if you're going to turn this number from scientific notation into standard form, what we're going to do is we're going to locate the decimal point. And since this is a small number, we are going to move the decimal point to the left as many places as there are powers of 10. So I'm going to move this decimal point to the left 9 places. So I'm going to move it to the left 1, 2, 3, 4, 5, 6, 7, 8, 9. So my decimal point has landed right here, and in all of those gaps, you guessed it, we're going to put zeros. So we have 0, 0, 0, 0, 0, 0, 0, 0. There we go. So your final answer, written in decimal form, is going to be 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then 6, 8. You do not need the 0 before the decimal point. I do personally like to put the 0 before the decimal point so people can clearly see that that is a decimal point and not just a stray mark from the marker. So I personally like to put the 0 in front of the decimal point, but you do not need to. But you have 8 zeros after the decimal point, 6, 8. Now, to write a number that is in standard form in scientific notation, you're basically going to do that process in reverse. You're going to figure out whether your exponent should be positive or negative based on whether it's a large number or a small number. And then you should figure out what power of 10 you would need. So for this next one, this is a very large number. So we're going to write it in the format of a times 10 to some power n. In this case, because the number is large, the power on 10 is going to be positive. So what I'm going to do is I'm going to locate the decimal point, and if there is no decimal point, you can always assume that there is a decimal point at the right end of the number. And what I'm going to do is I'm going to move that decimal point until the decimal point lands in such the way that it gives me a number that is between 1 and 10. And I'm going to keep track of how many places I have moved that decimal point. So here we go. I'm going to move it 1, 2, 3, 4. We're at 5 so far. I am not at a number between 1 and 10. So 6, still not at a number between 1 and 10. 7, and 8. So now my decimal point has landed at a number that gives me a number between 1 and 10. 8.243 is between 1 and 10. Now that'll be 8.243 times 10 to some power, and now is where you have to keep track of, okay, how many places did I move that decimal point? I moved that decimal point 8 places. So that is going to be 10 to the power of positive 8, and it is a positive 8 because this is a very large number. So written in scientific notation, we have 8.243 times 10 to the power of positive 8. So then for the next one, we're basically going to do the same thing. We're going to write this very small number in scientific notation. Now, since the number is going to be very small, the power on 10 is going to be negative. And like I said, scientific notation is the only context in which negative exponents are not only okay, but needed. So you're going to have a negative exponent on your final answer here. Don't worry about moving it into any denominators. You're just going to leave it. So what I'm going to do is I am going to locate the decimal point, and I am going to move that decimal point until it gives me a number between 1 and 10. Remember, the smallest that this a could be is 1. So this number a in front of here cannot be a number smaller than 1. And it cannot be a number 10 or larger. So let's move this decimal point and keep track of how many places we have moved it. So we have 1, 2, 3, 4, 5, 6, 7, 8. We're at 9 so far, but 0.65 is smaller than 1, so I'm going to move it 1 more to give me 10. So 6.5 is a number between 1 and 10, so that'll be 6.5 times 10 to the power of, how many places did we move that decimal point? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And since this is a very small number, this is going to be 10 to the power of negative 10. So 6.5 times 10 to the power of negative 10 is going to be your final answer. So that is the basics of exponent rules and scientific notation. So we are going to be using these rules throughout this chapter when we look at operations on polynomials, especially when we multiply polynomials together and we divide polynomials. So that actually wraps up the first 2 sections. Thank you all very much for watching, and I will see you in the next video when we finally start covering polynomials and operations on polynomials. So stay tuned for that, and I will see you in the next video. Bye-bye.